Almost 5 billion years ago, our young sun formed at the center of a gigantic cloud of gas and dust. In this swirling mass, dust and rock collided, forming ever larger clumps which, over the next few million years, became planets. At the same time, almost in the same place and from the same basic materials, two twin planets emerged very close to each other. An intelligent form of life would one day call them Planet Earth and Venus. A group of European planetary scientists located in Brussels, Cologne, Oxford, Lisbon, Nice and Paris, funded by the European Union, are working together for a period of 3 years, devoting all their energy to studying our extraordinary twin planet, Venus. This is the EuroVenus project.
On est un peu dans la situation des cartographes, des explorateurs du XVIIe siècle, XVIIIe siècle, qu'incarnent à merveille ces lieux ici, qui s'interrogeaient sur la présence d'un continent ou non dans l'hémisphère sud, autour de l'Antarctique, et qui finançaient ces immenses expéditions de James Cook pour les Anglais, de la Pérouse pour les Français. Et on est un petit peu encore à ce stade. Donc c'est quelque chose qui est extrêmement enthousiasmant de savoir qu'il y a encore tout près de nous un monde à cartographier, à explorer, dont on ne sait absolument rien. On ne sait pas si les volcans sont en activité, on ne sait pas si les roches traduisent la présence d'un océan primitif où la vie aurait pu apparaître dans les premiers milliards d'années de la vie de Vénus. Donc on s'intéresse beaucoup à toutes ces questions qui sont à notre portée, puisque c'est une planète toute proche de nous.
Their idea, combining space-based observations from the European Space Agency's Venus Express orbiter and ground-based observations from some of the biggest telescopes on Earth. What better way to start our Venusian journey than with one of the most striking phenomena on this planet? Its extreme temperatures. 450 degrees centigrade. That is the temperature of the surface of Venus due to huge greenhouse warming caused mainly by the massive carbon dioxide atmosphere. Higher up in the atmosphere, one finds cooler temperatures, similar to those on Earth. But how variable are these temperatures, and does this give us clues about atmospheric circulation? Scientists knew very little about how atmospheric temperatures on Venus varied until recently.
As you know, on Venus we have a very hot temperature on the ground. We have almost 450 degrees Celsius, and from this point on, if you go upwards, you see that it's getting colder. So the temperature is decreasing up to a certain point, which is called here the tropopause. And the same is true on Earth. You also have a warm surface on Earth, and then it's decreasing. But the difference is the atmosphere above. On Earth you have an increasing temperature above because you have ozone and you have a stratosphere. On Venus, you can see that you have a complete change of the behavior when you go upwards. So, as you can see, this is a particularly interesting region on Venus because you have, on the one side, you have this more or less boring-looking troposphere, and you have this interesting region above, and you have the clouds in this region, and therefore it's exactly the region we are interested in. We're using the subsystem, the radio subsystem of the spacecraft. Each spacecraft is equipped with such a radio link. This is done just to communicate with the spacecraft here on ground. And you can also dump data down to the ground with this. So you have just a single radio frequency coming from the spacecraft, going down here on Earth, and it's received here on one of the large antenna dishes here from NASA and ESA. And we are doing this in a so-called Earth occultation geometry. This means Venus Express is going behind Venus as seen from the Earth. And when it's doing this, this radio link has to propagate first to the ionosphere, and later on it goes through the atmosphere. And this leads to a certain bending of this radio link. And from this change in frequency, we can then calculate how dense is the atmosphere of Venus. And then it's quite easy to say something about the pressure and the temperature on Venus. So one of the interesting things we see in these data is a huge number of small-scale waves we see above the tropopause. It's not really clear what excites these waves. They are probably generated in this cloud layer, because this cloud layer is almost adiabatic. It means it's convective. This means that the air particles can move up and down, and they can probably also push the atmosphere above and below. And this might excite this atmosphere to move up and down, and then you have these waves. But there are also indications that some waves might also be generated by some topographic features here, by some large mountains that you see here on Venus. For example, we see many of these waves above this large mountain range, Ishtar Terra, in the high northern latitudes. The very interesting thing here is that how is it possible that waves generated here on ground can propagate to these altitudes, which are 65 kilometers or even higher. On Venus Express, it's also seen, for example, by the VMC camera. And then there's a nice paper from Arianna Picciali, which shows here that they also see a lot of these waves over Ishtar Terra in the high northern polar latitudes.
In the heart of the Alps, at 2,250 meters altitude, Arianna is going to continue her study of the atmospheric temperatures on Venus using one of the most powerful interferometers in the Northern Hemisphere, NOEMA.
The view is really fantastic. We are surrounded by the mountains and we are quite isolated.
By simultaneously using 6 antennae, NOEMA can achieve some of the performance of a single dish 760 meters in diameter.
And when we arrived this morning, the sky was wonderful and very blue, but for the moment a big storm started, so we are surrounded by snow and huge wind speeds of more than 100 meters per second, kilometers in fact. Per hour sometimes, so it's really, really high winds. So for the moment, we don't know if we will be able to observe. For us, this observation with NOEMA are extremely important because we have already observed Venus atmosphere in the past with Venus Express, but Venus Express died last year. So since more than 1 year, we don't have really observation on Venus, and the only way to observe Venus is the ground-based telescopes. With NOEMA, we can observe in the Zoom millimeter, which gives us the possibility to sound the mesosphere of Venus, which is a region very interesting because it's considered a transition region between the lower atmosphere and the upper atmosphere. It is characterized by very strong winds, a bit more like the one that we observe here. It's characterized by a temperature that changes a lot from one day to another. And so the idea is to arrive at a sort of climatology. So we need to understand why this planet evolved in such an extreme ways compared to her sister, the Earth. So I'm very excited about this measurement, and I really cross my fingers that tomorrow the weather will be good.
Space research takes time and incredible engineering, but also sometimes a little bit of luck. As the weather improves, the giant instrument is finally able to observe the atmosphere of Venus. It will take Ariana many weeks to process all the data. The results will be used to build up a more complete understanding of the atmosphere on Venus by combining them with those obtained by other members of the EuroVenus consortium. To measure the temperature of the upper reaches of the atmosphere on Venus, we need to get even closer. This is what the Belgian EuroVenus team did by placing on Venus Express an instrument they built called SOIR.
So that's actually a copy of the SOIR instrument, which was flying on board Venus Express. So what we were doing actually, the principle of the measurement is quite simple to understand. We see it every day when we look at the sun at sunset or sunrise. Actually, we were looking at the sun while it was setting or rising on the planet, and but from the spacecraft, not from the ground. And the principle of the measurement is that we first measure spectra of the sun while we look at the sun outside of the atmosphere, and then from the spacecraft we were seeing the sun setting, so we were measuring at different altitudes, and from these spectra we could deduce the composition of the atmosphere of Venus. From the composition there are some laws that allowed us to, physical laws that allowed us to retrieve the temperature profiles. So that instrument is very powerful. We have a lot of measurements, but it has one limitation, which is that we can only measure at the terminator, which is called the terminator, so the thin limit between day and night. So it's either 6 p.m. local time or 6 a.m. local time. These measurements were quite interesting. They showed two main things, actually. The first one, which is the most important, is the very, very large variability that we observed amongst all our temperature profiles. When you look at the temperature profiles on Earth, we observe variations, as we observe here on ground. One day it can be 10 degrees, the next day it can be 20 degrees. On Venus, the temperature differences that we were observing from one day to another were varying up to 50 to 60 Kelvin, which is very, very large. The second one is something that we did not expect at all, which is a very, very cold layer that we observed at an altitude of about 120, 130 kilometers. Actually, the temperature is dropping at these altitudes at the level of the terminator, so at the limit between day and night, down to temperatures of 80, 90, 100 Kelvin, which means minus 170, minus 180 degrees Celsius. It's almost the temperature, it's very close to the temperature of solidification of CO2. So we did not observe it, but we could have CO2 ice actually at these regions. And it's quite amazing because we know that Venus is very warm, the warmest planet of the solar system, which has an atmosphere, not talking about Mercury. And there we observe on that same planet one of the coldest temperatures amongst Venus, Mars, and the Earth. So this is quite an incredible result that we had. We did some investigation in order to understand what were the physical reason of this temperature. And actually it is due to that same CO2, so the CO2 that is heating up the lower parts of the atmosphere at this altitude has some properties that makes it cool down the atmosphere. Actually, it's mostly due to the collision of the CO2 molecules with the atomic oxygen molecules, which de-excitate the molecules and actually pump up the heat and cools down the atmosphere. And that's probably the reason why we don't have that effect on Mars or on the Earth, because we do not have so high concentrations at these altitudes of CO2 and oxygen. So that's probably the main reason of why we have these temperatures.
While Arnaud Mayeux is studying solar occultations using Venus Express, another kind of solar occultation has been used by EuroVenus scientists, this time visible not from Venus Express, but from Earth. planet Venus, dancing between the Sun and Earth, showing us for a brief moment the true size of the solar system around us, but also revealing the nature of its mysterious atmosphere. This is the transit of Venus.
The transit of Venus is a rare event, occurring twice per century on average. And so rare that basically a person just have one or two opportunities in its life to observe it. And what it is simply the small disk of Venus passing in front the disk of the Sun. The history of observations of the transit of Venus is fascinating because it was first observed in the 17th century, and then soon the astronomers realized that it was a unique opportunity to try to determine, to solve one of the most important questions at the time, the scale of the whole solar system, just by measuring the distance between the Sun, Venus, and the Earth. This was so important at the time that they organized huge expeditions. It were years of preparation and travel to go transport instruments toward hostile countries far away in the Pacific, toward populations that were poorly known, install the instruments, hoping the weather was good for just minutes of time during the transit. It's quite incredible to think that in 1882, when this observatory was founded, was being built, Henri Perrotin, his first director and astronomer, went to Patagonia, organized an expedition to observe the transit of Venus in 1882, 6th of December. Here you have the official registers of the mission, where all the information are copied, and it starts by describing the arrival in Patagonia till the day of the transit on December 6th. And on that very day, the note starts, the sky is completely covered. In the morning, it rains. But at a certain moment, the transit has already started, and they can see Venus half on the disk of the Sun. And they start to measure the event. I realized in 2004, with the first transit I was able to see of Venus, that there was something in it that was possible to exploit, to study Venus itself. This thin aureole of light that was already seen in the 18th century, first in 1761, by Lomonosov, a Russian astronomer, it is visible only at the entrance and the egress of Venus, so just at the beginning and the end of the transit. 20 minutes at the beginning, 20 minutes at the end, about. So it's a very short time frame that we can exploit to probe the atmosphere of Venus in the layers where this light passes and produces this phenomenon, which is also called the aureole of Venus.
The aureoles of Venus. How can anyone observe something so faint in broad daylight without being completely blinded by the sun? Paolo's team and the workshop of the Côte d'Azur Observatory took up the challenge.
We exploited the idea of using a coronagraph. That is a device that is capable of hiding the light coming from the solar disk to better show what is close to the sun. It was built essentially here at the Observatoire de la Côte d'Azur. You can see here how the device looks like. It was inserted at the focus of a simple commercial telescope, and the core of the device is this cone here, which is a solar occulter, it is called. It has exactly the same size of the sun in the focus of the telescope. So it can completely hide the light of the sun, and we can easily see, close to the sun, the light of the aureole this way. So I was lucky to have here 9 of those instruments in Nice, assembling them. And then a few days later, it was quite impressive because they were traveling all around the globe. And I was receiving pictures of people in Australia, in Japan, in India, with those telescopes around the world. It was pretty amazing, just a few days after. And then the right moment came. And it was a fascinating experience, because when I first realized that everything was going well, and we started seeing on our computer screens the auroral forming while Venus was approaching the Sun, I knew at that right moment that we were being successful with the experiment. And soon afterward, I realized that, wow, we really did that. And it was once in a lifetime, it was gone, just gone. And it was a kind of strange impression. And I say, after with time passing by and looking back to those exciting moments, I really realized completely how great this opportunity was to see the transit and to be able to have an experiment built for that, even if it was done with a simple instrument, basically, but targeting real science.
For almost 4 years, Paolo has been analysing the data from those incredible 40 minutes. From thousands of images captured, he has managed to make them come alive and reveal new details about the atmosphere of Venus.
And for example, this image showing Venus against the solar corona also shows this very, very bright aureole, because there it is the polar region of Venus where the clouds ends at a lower altitude. So there is more transparent space for the light to pass through this atmospheric layer, meaning that you have more light, the aureole is brighter, and we can see it when Venus still has to begin the transit. So we were very lucky, because during the transit, the Venus Express satellite of the European Space Agency was observing Venus, basically at the same time. So when we were observing from the Earth, seeing the aureole all around the limb of Venus, and the Venus Express was performing a very specific measurement, very close, of course, with much detail. So at the same time, we have a reference point, that is the latitude observed by Venus Express, that allows us to control what we are doing, and the measurements from our ground-based experiments, in which we see all the latitudes together. For the first time, we are able then to extract the information on the physical conditions of the atmosphere for all the latitudes at the same time. These observations of the aureole are the demonstration of a reality that we forgot sometimes. Namely that even when we build space missions and huge telescopes and the probes that go to the planets very close to them to observe their surface in great detail of their atmosphere, but even then, the instruments that are on the ground, far away, maybe sometimes small instruments, still have information to bring, still can give a contribution. And so the two approaches are completely not in conflict, but complementary, because they see different things, different level of details, but both are important.
Science is more than mere calculations and numbers. It's about determination and curiosity, about putting all your energy looking in one direction without being sure of what you will find. In about 100 years, the next transit of Venus will without a doubt once again bring its share of discoveries and remind us of the amazing scale of the elements around us.
1978 was a very busy year for space science. One of the most ambitious missions involved two Pioneer spacecraft that were launched toward a rendezvous and landing on this planet, Venus. Scientists believe that by studying the weather of Venus, they can learn about our weather here on Earth.
What this NASA probe discovered on Venus a year later is amazing. A hurricane-like vortex at the south pole of Venus, bigger than any seen on Earth. Almost 30 years later, thanks to the latest European spacecraft orbiting Venus, Venus Express, and some of the biggest telescopes on Earth, EuroVenus scientists are beginning to understand one of the strongest forces on our neighbouring planet: winds.
Il est 5h30 du matin. On a fait le tour de la planète pour venir jusqu'ici. Il fait jour en Europe, il fait nuit ici. Et Vénus vient de se lever derrière nous. C'est une planète difficile à observer parce qu'elle est toujours, malgré sa brillance, à proximité du Soleil. Et très peu d'observatoires permettent cette observation de jour. Et nous avons cette chance inouïe d'avoir à notre disposition l'outil exceptionnel qu'est le télescope Canada-France-Hawaï, qui nous permet à la fois de mesurer les vents sur Vénus, mais aussi de l'observer de jour. Et donc nous sommes dans cette situation à quelques heures de la mise en service du télescope. Je vois que Vénus continue à monter à l'horizon, donc nous allons monter maintenant au sommet. Pouvoir aller en voiture à 4200 mètres d'altitude au centre du Pacifique, sous un ciel d'une pureté absolument cristalline, c'est une expérience extraordinaire. Tous les astronomes qui ont observé depuis une quarantaine d'années, disons, dans ces très très grands observatoires situés au sommet du Mauna Kea, ressentent cette incroyable sensation d'être posé au centre du Pacifique sur un volcan qui fait au total 11 000 mètres de haut entre le bassin du Pacifique et le sommet du Mauna Kea. Et cette sensation de tutoyer le ciel et d'être au bras de cet univers qui nous entoure dans des conditions exceptionnelles.
En ce moment, nous sommes en train de voir la position de Vénus sur le foyer de miroir primaire du télescope. Ça, c'est un peu dangereux et même un peu critique parce que le Soleil, c'est pas vraiment très écarté de Vénus et pour cela, nous pouvons avoir la lumière du Soleil entrer directement dans la coupole et ça, c'est très dangereux. Pour cela, nous avons beaucoup de sécurité. Nous avons là-haut, dans la coupole, les Sun Watchers. Alors, nous avons 2 personnes qui sont tout le temps à voir s'il y a des lumières directes ou réfléchies qui peuvent abîmer ou être si près du miroir.
Okay. Okay, David, we're starting to get some sunlight on the secondary ring.
Stand by for dome rotation, clockwise.
Dome clockwise.
I don't have a picture of it yet, but we're in good position. Sun watchers, please stay on duty, and we're going to work on inquiring Venus.
Can we enter the other coordinates manually? I think there is an offset by 1 Mach-minute for some reason.
Counterclockwise.
Il y a un problème de guidage, de pointage de Vénus pour l'instant.
Was my concern.
Sun watchers, stand ready. We are ready to slew to in position for Venus.
Standing by.
For almost 6 hours a day on 5 consecutive days, Thomas is going to measure the winds on Venus. Earth-based measurements enable scientists to make a complete coverage in latitude, longitude, in local time on Venus. The purpose is to obtain a comprehensive modelling of the planet winds on a global scale and to compare it to climate models.
Un télescope va former l'image de la planète au ce qu'on appelle le foyer, qui est donc une image de Vénus assez étendue, qui va nous permettre, avec la fibre d'entrée de l'instrument que nous utilisons ici, de prélever la lumière du Soleil réfléchie par Vénus et d'en mesurer le décalage spectral, c'est-à-dire la vitesse. Donc il n'y a pas de guidage automatique. Donc tout ce travail est fait manuellement par l'astronome qui va utiliser une sorte de maquette de Vénus plaquée sur la planète, comme vous avez vu tout à l'heure, et qui va nous permettre de se positionner en différents points de la surface. Alors c'est très important, pourquoi ?
parce que les vents ne sont évidemment pas les mêmes à l'équateur, dans les régions tropicales, le matin, le soir, sur Vénus, exactement comme sur Terre. Et donc on va avoir une climatologie de ces vents, et il va donc être nécessaire d'acquérir des séries de ces mesures en différents points, et nous sommes le seul endroit à faire ces mesures sur Terre. On peut se représenter l'atmosphère de Vénus comme un océan. C'est une atmosphère extrêmement épaisse, extrêmement à très haute température, mais extrêmement visqueuse même dans sa partie la plus basse, qui va donc avoir un rôle pour transporter la chaleur et donc la température tout au long de la planète. Un petit peu comme les océans terrestres ont un rôle très important dans la machine climatique terrestre, en quelque sorte, comme d'ailleurs sur les autres planètes aussi. Donc étudier les vents, ça permet d'étudier la distribution de la chaleur qui est donc apportée par le Soleil pour faire fonctionner la machinerie climatique, disons, de la planète. Ce que j'essaye de trouver, moi, ici, c'est comment est-ce que les données que nous avons sur Vénus, qui sont très partielles, contrairement à d'autres planètes, à la Terre, où nous avons des satellites en permanence, les données sur Vénus, c'est de temps en temps, et puis il faut essayer de les replacer les unes par rapport aux autres, comment ces données vont pouvoir alimenter les modèles climatiques de Vénus et nous mieux comprendre cette planète pour le futur.
Almost 12,000 kilometers away from Hawaii, another kind of work is being done at the Paris Observatory. This time, based on data collected directly by the Venus Express spacecraft and concerning the giant polar vortex on Venus.
On savait que Vénus avait déjà un vortex polaire sur le pôle Nord, et sur Venus Express a montré qu'il y a un vortex polaire aussi au pôle Sud. Ça a été une énorme découverte. Et le grand mystère, c'est savoir ce qui crée ce vortex. On peut imaginer que c'est la circulation globale, la circulation vraiment à l'échelle planétaire qui crée le vortex polaire. Et ça sur les deux pôles. Vénus a une circulation très symétrique où il y a un vent qui se déclenche vers l'équateur, qui remonte et puis qui redescend près des pôles. Et c'est cette structure du vent qui va produire des mouvements d'air qui vont créer les vortex. Et ce qui est extraordinaire pour cette structure, c'est qu'elle change tout le temps. Elle change d'un jour à l'autre. La forme du vortex change. Et c'est quelque chose qu'on n'arrive pas encore à comprendre, ce qui produit ce changement continu d'une structure d'aussi grande taille. Il fait environ 3500 km de diamètre. Il est aussi grand que l'Australie, par exemple, et il est centré sur le pôle Nord et sur le pôle Sud. Donc le vortex polaire vénusien est vraiment un ouragan qui ne s'arrête jamais. Il est toujours là en permanence et il est justement créé par le réchauffement par le Soleil.
Meanwhile, in Hawaii, another kind of work is being done at NASA's IRTF observatory, but this time measuring the chemical composition of the atmosphere in order to address one of the major scientific questions raised by the study of Venus. Is our neighboring planet volcanically active?
Vénus est recouverte d'une couche de nuages extrêmement épaisse qui nous empêche d'ailleurs d'observer sa surface à l'œil nu. Et par des observations répétées depuis maintenant presque des siècles, on sait que les molécules, ces nuages sont composés d'acide sulfurique, extrêmement peu sympathique donc pour aller y vivre. Cet acide sulfurique, il a été formé par combinaison de deux molécules essentiellement qui sont SO2, dioxyde de soufre et vapeur d'eau, H2O. Et c'est pourquoi nous avons attaché donc toute notre attention à l'étude de ces deux molécules. Et pour ce faire, nous utilisons un spectromètre qui s'appelle Texas, qui est monté au télescope donc depuis une semaine maintenant. Alors je suis toujours sous le télescope et il est possible de voir Vénus en plein jour en prenant des repères sur le télescope qui permettent de s'aligner. Alors ici, je mets mon œil en face d'un premier repère qui est situé sur la partie proche de moi du télescope, et j'aligne avec un second repère qui est au bout du télescope de l'autre côté. En alignant ces positions, je tombe sur Vénus et je le vois. Ah ben c'est très émouvant, c'est très émouvant. Il serait évidemment impossible de le voir, de voir la planète, s'il n'y avait pas ce dispositif, parce que la lumière de Vénus, comparée à la lumière du ciel, évidemment, ne permet pas de la détecter sans un repère précis. Quand on a commencé à observer, c'était en 2012, ça fait donc exactement 4 ans maintenant. On observe, et c'était la première fois que des observations de ce type étaient faites, et on s'attendait un peu naïvement à ce que les observations des deux molécules suivent la même évolution temporelle et spatiale. En fait, ce n'est absolument pas le cas. Dès la première mission, on s'est rendu compte que les cartes de la vapeur d'eau sont relativement homogènes sur le disque et varient assez lentement dans le temps, alors qu'au contraire, le dioxyde de soufre a des variations extrêmement fortes le long sur le disque de Vénus. Le problème, c'est qu'avec cette couche d'acide sulfurique qui est extrêmement épaisse, on ne sait pas, on n'arrive pas à savoir exactement ce qui se passe en dessous. L'origine de SO2, on pense que ça doit être du volcanisme. On sait qu'il y a eu du volcanisme sur Vénus dans le temps, parce qu'il y a eu des images radars, donc qui permettent de sonder au travers des nuages, qui ont montré que Vénus était couverte, la surface de Vénus est couverte de volcans. Mais ce qu'on n'arrive pas à savoir, et ce qu'on aimerait bien savoir, c'est si le volcanisme est encore actif aujourd'hui. Et si on arrivait à mettre en évidence une très forte évolution du SO2, on pourrait vraiment essayer de corréler ça à un événement volcanique présent. La difficulté de relier ce qui se passe au niveau des nuages à ce qui se passe à la surface de Vénus, c'est qu'il y a une pression à la surface de Vénus qui est à peu près 100 fois la pression atmosphérique terrestre. Autrement dit, s'il y a une plume volcanique qui est émise à la surface, elle va être écrasée par toute cette masse de gaz. On peut prendre comme équivalent ce qui se passe sur la Terre en imaginant qu'il y ait une éruption au fond des océans. À côté d'Hawaï, ici, supposons qu'une nouvelle île soit formée, eh bien, on ne verra rien à la surface de l'eau. Eh bien, on est un petit peu, si vous voulez, dans cette situation-là.
Observations that are made from the Earth can be used to localize plumes or regions where the concentrations are higher or lower, give a direct view of what's happening at that moment of the observation. We have developed another instrument, another kind of instrument called SOIR, solar occultation in the infrared. And this instrument is on board Venus Express, is a mission around Venus.
When an instrument is sent into space, a copy is always kept by the makers so that they can reproduce any problem that might happen during the mission.
What we can say is that both species are very, very variable in terms of time, short-term times, and in terms of altitudes. For example, for the SO2, our observations seems to indicate that there is a source of sulfur higher in the atmosphere. It's highly improbable that there could be a source of sulfur so high in the atmosphere. So the volcanic activity could explain what we are observing concerning the SO2 abundance.
Scientists proceed cautiously. These variations in SO2 abundance are not necessarily caused by active volcanism because of complex chemical cycles in the clouds. However, measurements of SO2 from another instrument aboard Venus Express showed a striking pattern.
Those observations are very interesting because they show that at the beginning of the mission, right at the start, there was a large increase in the SO2 abundance observed, and which decreased during the mission. And similar observations had been done in the past by other missions who saw the same behavior, a large peak of SO2 abundance and then decrease. And one of the explanations, of course, could be volcanic activity. You could imagine that there would be a volcano expelling SO2, you have your peak, and then decrease while SO2 is mixed in the atmosphere. That's one of the explanations which could be possible.
It's great walking around on the surface of these lavas because you get a sense of what it might be like walking around on Venus. Except, of course, for the temperature on Venus. Remember, the surface temperature is 450 degrees, so we wouldn't last long. When the Soviet landers first arrived at the surface of Venus, they started taking some pictures. This is back in the 70s and early 80s, and they revealed some black rocks everywhere, what seemed to be things very much like these lavas, which made people think that there could be lots of volcanic activity. And that suspicion was confirmed when the Magellan radar mapper arrived in the 90s and revealed that yes, there were indeed volcanoes all over the surface of Venus. But although we know that there are things shaped like volcanoes all over the surface of Venus, we don't know if they're active. And so that remains one of the most important questions today is our neighboring planet geologically alive or dead? So with Venus Express, we've had a few interesting hints about this. One thing you can do is you can look for how black the lava is. So a lava like this is really recent in geological terms. It's very black. Over time, it'll change color. It'll get less black. And so on Venus Express, we've seen that the blackest areas of the surface are right next to some particular volcanoes in spots where we think there's likely to be volcanic activity. So that's a hint at geologically recent volcanism. Another thing we can do from orbit is map the surface temperature because if the planet's geologically dead, you'd expect everything to be roughly the same temperature, or maybe the highlands are colder than the lowlands, as you find on Earth. But if activity is going on today, if volcanoes are active today, we might see lava lakes, we might see hot gases emitted from a vent and things. And so Venus Express was not designed to do this. It can only do it at some very particular times in its orbit, and it didn't get lots of information about this, but there are some images where we do see hot points arising on the surface and then cooling off again. So that might be the smoking gun, that might be volcanism in action, but it'll take future missions to really answer this question.
Imagine a planet covered with active volcanoes, lava flows, and plumes of volcanic gases. Recent observations show that this is increasingly likely to be the reality of our neighbouring planet, Venus. The Earth, the planet that we know so well, lying just under our feet, and 160 million miles away, its mysterious sister, Venus. Today, scientists are looking at the future of Venus exploration with excitement. They are convinced that the answers to their remaining questions are soon to be found.
Venus and Earth are very different today. The climate they've ended up with is very different. And one of the main differences you can see behind me, water. Liquid water, we have lots of it all over the surface of the Earth, whereas on Venus it's too hot today to have liquid water. It's 450 degrees on average at the surface, and that's far too hot. But a long time ago, when the planets were forming, they probably weren't so different. The planets were formed, the terrestrial planets, Earth, Venus and Mars, were probably formed around the same time out of the same materials. And initially when they formed, they would have had a magma ocean due to all the heat of formation. And eventually that magma ocean would have solidified so that you have solid rock surfaces, solid rock crusts. But at that point, it's still very hot. You still have atmospheres mostly of carbon dioxide and lots of water in the form of steam because it's too hot to have liquid water. And on Earth, it cooled just enough to allow that, that water to liquefy on the surface. And once you have liquid water on the surface, then through various reactions, that liquid water can react with the carbon dioxide in the air and with various rocks to lock that carbon dioxide up in rocks, carbon-bearing rocks on the surface. These are things like limestones, chalks, which you find all over the world. And because of that, we're left with very little carbon dioxide in the atmosphere. Happily, because carbon dioxide, for example, is poisonous to us. So this story about the history of water on Earth, the history of the climate on Earth and Venus and terrestrial planets in general, and how unusual it is to end up with such a perfectly adapted planet for us, is something we're really interested in finding out, particularly now that we are aware and we know that there are thousands, millions, billions of planets in the universe. How many of those are going to be Earth-like? How many of those are going to be Venus-like? How many of those are going to have liquid water on the surface? So by tracing the differences in formation and evolution of Earth and Venus and Mars and comparing them, we can find out how unusual it is to end up with planets like the Earth.
To our current knowledge, no other planet offers environments as diverse as those of planet Earth. To continue making progress in Venus exploration, scientists need new ways of investigating. But what are their choices? For Arnaud Mailleux, from the Royal Belgian Institute for Space Aeronomy, the answer is clear.
The best way, but it's usually quite hard to get, is to have new missions to the planet. That's usually the best. You can either do measurement from the Earth, but the problems of doing measurement from the Earth is first, there is a very good point from ground-based measurements is that you can do it as many times as you want, as long as Venus is in the sky. But we are very far away from Venus, so we do not get very localized observation measurements. The measurements we get usually cover large regions of the planet. The best way is to send, of course, another spacecraft. That's really exciting. That's really something we are looking forward to.
For me, one of the main important things that we will have to answer in the near future is really, can we prove that there are volcans and active volcans on Venus? And to do that, the problem is that we have to look below the clouds. And the clouds are effectively absorbing a lot of light. So you need a specific instrument to look below, look at specific wavelength to go down. And that's something that we are very interested in. We are in the process of developing a new instrument based on SWAR, based on the instrument that we have developed for Venus Express, so building on heritage, but looking down and below the clouds. We are preparing it to be ready for the next call, the next proposition to go to Venus.
Going back to Venus with a new space mission. This is in the mind of every Venus scientist. To discuss this, and all things Venus, a world conference has been organized in Oxford University, gathering for 5 consecutive days the best experts from around the globe.
So here we are at the Venus 2016 conference in Oxford. We are now in the Museum of Natural History of Oxford University. We're 2/3 of the way through. We've heard some great results about, which is still coming from Venus Express. We heard some new results from the Akatsuki mission, which has just arrived at Venus, and it's only just started taking science results. And none of those results are publicly released yet, so we feel really privileged to have seen some of those first images.
We Japanese Akatsuki team has a very strong relationship with the European Venus Express team. And actually, Venus Express and Akatsuki are a kind of twins. And so we can continue this collaboration. Venus Express is a polar orbiter, but Akatsuki is an equatorial orbiter. This is very similar to the meteorological satellite of Earth.
So what can we expect in the near future? We have 2 excellent proposals from our NASA colleagues for the Discovery round. And those proposals, one of those is focusing on the surface science, on mapping the surface with excellent resolution. The second proposal is focusing on the measurement of the isotopes of the noble gases, which will open the door for understanding of the history, not only Venus, but of the entire inner solar system. So I think that these things are definitely, if even one of those is going to happen, then Venus community will be absolutely happy and will really be looking forward for new results and new discoveries.
Dans ce musée merveilleux, on peut voir de nos propres yeux que la nature est variée. Elle est faite d'oiseaux, d'animaux terrestres, de poissons. Une planète, c'est extrêmement complexe également. Il y a l'atmosphère, il y a la surface, il y a l'intérieur, le volcanisme. Donc nous pensons que la prochaine étape de l'exploration de Vénus, après cette très longue mission, cet extraordinaire succès sur l'étude de l'atmosphère, devrait plutôt se consacrer à la surface et à l'intérieur. Donc c'est un petit peu la nouvelle étape, poursuivre cette exploration, ce décryptage de notre voisine par tous les moyens possibles. Vénus Express, à la surprise générale en quelque sorte, a relancé de manière extrême l'intérêt pour la planète Vénus. C'est une mission extraordinairement à succès. Et finalement, cette opération a déclenché un véritable engouement pour cette planète pendant 10 années. Et aujourd'hui, on a une très très forte communauté et ça a déclenché une sorte d'éveil, d'intérêt international pour la planète. Au Japon, il y a une mission actuellement en cours d'opération autour du Japon. À la NASA, des appels d'offres qui ont été pour l'instant presque à succès, puisqu'on est présélectionné pour aller... Donc il y a eu un effet, je dirais, de boule de neige. Et nous sommes très heureux que l'Europe ait pu contribuer à cette relance pour plusieurs décennies, nous l'espérons, de l'exploration de Vénus.
From now on, nothing can stop the march of science towards Venus. Little by little, scientists are lifting the veil on this little dot that we see in the sky every morning and every night. What does it take to be Venusian? The answer could be patience, ingenuity, imagination, and an insatiable hunger for understanding what is beyond our world.